Graphing's never the answer, but it's a way to get the answer. And you've seen, or you will be able to see, the SageMath, the online computer approach to graphing. But we're going to do some graphing by hand and based on a very, very basic principle. And the basic principle is the mean value theorem, which one of my friends calls the mean old value theorem, but it's not. It's a really nice theorem. The thing is the way the books state it, not just any of the books that we're using, mine's the exception. The way the books state it is not very useful, and what is useful is a consequence of the mean value theorem, which I'm going to put down here, which is that if the derivative of a function is positive in an interval, then the function is increasing. So you got to read this very carefully because the signs are kind of small. The derivative is the smallest possible sign that you can make. And so, but this says y prime is greater than 0, means that y is increasing. If y prime is less than 0, then y can't be increasing. And so that tells you something about the behavior of y. So you can start to get this kind of up, down, up, down, up, down approach to looking at what the graph looks like. Once you have the graph, you can find the maximum and the minimum, or the maxima and the minima if there are more than one, and they become quite obvious. And the work to find maximum and minimum gives you the graph anyway. So there's an extension to this that people have found confusing, and so let me kind of run it by you a little bit, which is this. I'm going to do the parentheses first because that is the way to do any kind of mathematical writing. And so I'm going to say, let's leave it out for a second now. Is positive implies, well, we're leaving it out again, is increasing. But this time, instead of doing this to y, I'm going to do it to y prime. So y prime greater than 0 means that y prime is increasing. So whatever the function is, if the derivative is greater than 0, then the function is increasing. If the function comes with a backstory, oh, it happens to be the derivative of something else, well, it's still true. The mean value theorem implies that if the derivative is positive, then the function is increasing. And if the derivative is negative, then the function is decreasing. Now, what I wrote here is a little awkward. It's got lots of colors and parentheses and so forth and so on. But so normal people call that y prime, the second derivative. So if y prime is greater than 0, then y prime is increasing. And you can draw a new conclusion from that, which is that y is concave up. And the picture there is way simpler than most of the books make it look, which is, I find disappointing. But if I look at a graph of some function y, so there's a graph, it's concave up. No tick marks, no axes, no nothing. Concave up is concave up, concave up. And if you look on the left side of this graph, y prime is negative. And on the right side of this graph, y prime is positive. And how do I know that? I know that because y prime is the slope of the tangent. And so I draw the tangent line and say, oh, that slope's positive. Oh, that slope's negative. Now, this is a deep thought that does not require much computation, but it can be a insight kind of thing. If something goes from being negative to being positive, that's an increase. Negative to positive is an increase. Positive to negative is a decrease. And so what you're seeing in this concave up graph is that y prime, the slope of the tangent line, is increasing. So that is a visible manifestation. So y prime is increasing. Okay. So let's get to the good stuff because there's another trick that's very, very important. The purpose of this is to reduce the amount of algebra that anyone has to do because algebra is hard and is mistake prone. And so we're going to try to eliminate some of the algebra. So I'm going to take a function. I'm not writing it as a function, I'm writing it as a graph, but we can go back and forth. Y equals blah, 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 f of x equals blah, 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 blah. Same thing, just sometimes it's less writing to say y. And I'm going to say this is x squared times e to the minus x. So this is a function that is on another video being done by an automatic system by SageMath, but we're going to do it by hand and see what happens. Y prime, y prime, to do that, you've got a function that's a product. It's x squared times e to the minus x. And so you have to use the product rule. And so in the very important strategy of doing the parentheses first, the product rule says the derivative of a product is the derivative of the first times the second plus the first times the derivative of the second. And now I can just cut and paste. So in the first set of parentheses, in pink goes x squared. It's almost like a boxing match. In the far corner, in the pink trunks, is x squared. There it is. I've just copied it in. It's in pink. And in blue, this sounds like the battle of the sexes, doesn't it? Or else politics in the United States. We got the pink versus the blue. Okay. Anyway, that's e to the minus x and e to the minus x. So notice I'm organizing, then calculating. This is the right way to do algebra, is to organize, then calculate. And so I've done the parentheses first. Okay. And these are derivatives that we know how to do. And so I'm going to just start doing them. Derivative of x squared is 2x. And that's going to be multiplied by e to the minus x. Don't try to do this on the fly. Organize, then calculate. And then we're going to have x squared is x squared. We're not doing anything to that. And the derivative e to the minus x is one of the most commonly misdone derivatives because you have to use the chain rule. And so what pops out of here is a minus sign minus e to the minus x. Chain rule says with a composition, you take the derivative of the two functions that were composed. One of them was negation, its derivative is minus 1. And the other is exponentiation, its derivative is itself. And you just multiply the two derivatives of the composing parts. Okay, so we have to do we haven't done much algebra yet, but we have to do a little algebra here and notice that when I did this derivative, I have a common factor of e to the minus x, e to the minus x, e to the minus x. So I'm going to pull out the common factor, and what's left over is 2 minus x squared. Excuse me, 2x minus x squared. So we got a 2x here and an x squared there. Okay. This is where things can get complicated or they can get easy. Every book I've ever seen, except for mine, makes it very complicated by starting to have you do this and that. First of all, e to the minus x is never negative. We are interested in the sign of the derivative. And if you want to know what the sign is, you take a positive factor, and that won't change the sign. So for the purposes of looking at the sign, I don't care about the e to the minus x. And the other factor is 2x minus x squared, and that is an upside down parabola. So let me just label this as sine of y prime. So it's an upside down parabola. I guess in Australia it's right side up, eh, mate? Okay, fair dinkum. Anyway, and the roots, this 2x minus x squared is easy to factor. It's a factor of x. And so the roots are at 0 and 2. So that tells me the sign of y prime. It's negative, then it's positive, then it's negative. That means that y is decreasing, then increasing, then decreasing. And so without doing a lot of calculations or test points or other things that I'm not going to tell you to do because I've never actually done them in real life, you know this is one of your basic functions, and you know basically what its plot looks like. You don't need to use this to design a bridge. You just need to know the sign. Okay, so that was the first trick. Ignore factors that are known to be positive. Okay, so the second trick is this, is we're going to come back and we're going to take the second derivative. And so now you can't ignore the other factors for the second derivative. You have to go back to the first derivative that you had. And so it's easier to do the unfactored form. That's just a fact of life. And so there's something very important to have here, which is that we've got, I'm going to do this nice and slowly. Some people say I'm doing extra steps, and I say, no, you're skipping steps. And there's a big difference there. And so what we have here is I'm doing the parentheses first. And what I've done is taken out a factor of 2, and then I said, oh yeah, I'm going to take the derivative. Yeah, one of these days. I'll get around to it. Don't nag me. I'll get around to it. I'm going to take this derivative one of these days. But now comes the second piece of important insight. The second term here is there's a negative x squared e to the minus x. Well, you know what? We already did that derivative. This is the recognizing the pattern part that comes when you don't simplify things too much. I need to take the derivative of minus x e to the minus x squared e to the minus x squared. Well, I already done that. So I'm just going to copy it in. So when I copy it in, it's just what we had before, 2x e to the minus x minus x squared e to the minus x. Well, the writing's getting kind of small, but it's there. Remember, I'm going to scan this so you can look at it. Okay. So now I have to do the simplification. First thing to notice is that every term has a factor of e to the minus x. Every single term has a factor of e to the minus x. So I'm going to pull that out. So e to the minus x. And that just gives me the warm, fuzzy feeling because that's a factor that is never negative. So this does not affect the sign. Okay, so what's left over, we have to be a little bit careful here. Oh, I never actually took this other derivative. Ooh, screaming sacks, I used macaroni. Anyway, so 2 times e to the minus x e to the minus x, minus 2x e to the minus x squared e to the minus x. And I believe I've done this algebra correctly. It agrees with what I have in my notes, so it must be correct. Anyway, so now everything has a factor of e to the minus x. And putting things together, we've got 2 minus x minus 2x plus x squared. This is the kind of fancy algebra that you have to do. You've got a minus times a minus, so that's a plus. So you end up with this, and let me just kind of neaten that up a little bit. I've got this e to the minus x, which I'm going to ignore, and then I have 2 minus 3x plus x squared. Okay, factor I'm going to ignore, and so the sign of the second derivative is the sign of this quadratic, which we can get at by graphing a parabola. Now this is a right side up parabola, and so when I look at the sign of y double prime, I have a right side up parabola, and you're going to have to check me on the factoring, but I'm factoring this correctly. Its roots are at 1 and 2. And I really don't care about anything else about the parabola other than its sign. So the signs of the second derivative start off positive. That means the function's concave up. Then the sign of the second derivative is negative. That means the function's concave down. And then the sign of the second derivative is positive. That means that the function is concave up again. And so just by the signs, we haven't put in any points. We haven't had to factor any more than was necessary. And by ignoring the always positive factors, we simplified the factoring quite a bit. to just factoring quadratics. Remember, you can always factor a quadratic with the quadratic formula. It may not be pleasant. I happen to like it, but you may not find it pleasant, but it always works. So we have to be grown-ups about it. Okay. So now let me give you kind of an overview of what we know about this function based on the sign of the derivative and the sign of the second derivative. And the places where interesting stuff happens is where the sign of the derivative changes. Those are called critical points. And where the sign of the second derivative changes, those are called flexes or points of inflection. So we're interested in the points 0 and 2 and 1 and 2. So well, that means we're just interested in 0, 1, and 2. So I'm going to make this kind of conceptual diagram, 0, 1, 2. And the derivative part is negative to the left of 0. So I'm not interested in the derivative. I came here to talk about the function. So the function is decreasing. And then between 0 and 2, the function is increasing. And then after 2, the function is decreasing again. So I am just indicating that on this diagram. It's not a graph, it's a diagram. It will turn into a graph. Y prime is negative, so y is decreasing. Y prime is positive, so y is increasing. Y prime is negative. Okay. And then with the concavities, let's see, the concavities changed at 1 and 2. So to the left of 1, we were concave up. Between 1 and 2, we were concave down. And after 2, we were concave up. So we just write up, down, up. So there's that. So now I'm going to fill in the shape. And the shape is going to be, it's not enough to build a bridge, but it gives you a good idea what's going on. And you can find the maximum, you can find the minimum, you can find the flex. So, and I'm just going to superimpose this on here. It's not going to be the prettiest thing you've ever seen, but there we go. So we start off with the function being decreasing and concave up. And so the shape is boom, boom, boom. Decreasing concave up. Now the function changes to being increasing concave up. So I can throw in the shape. And now the function is increasing and concave down. I'm kind of run into my other stuff there. So, sorry. And then the function is decreasing and concave down for a while. And finally, in the end, it is decreasing and concave up. So the shape we get, I'll kind of do this off to the side, is kind of like this. That's the shape. Over here. Sorry, I didn't leave enough room. So there's this shape, decreasing concave up, increasing concave up, increasing concave down, decreasing concave down, so forth and so on, as spelled out in this diagram. So this is the basic graphing thing. 2 big techniques to make it easier that will work in almost all the problems that you'll ever bump into in your life. They won't work in everything, but they'll work in a lot of problems. Ignore positive factors. Ignore negative factors too, only that makes things negative. So ignore positive factors and only look for the signs. And if you do that, and then always, as usual, do the parentheses first, you'll find that a lot of the difficulties that you see about graphing, you didn't need to do those. I don't know why they make you do those. You don't have to do those to graph. I mean, eventually you're going to have to pin down some points by plugging into the function. But to get the basic shape of the graph, which is often what you need, then all you need to do is look at the sign of the derivative and the sign of the second derivative.